Okay,
and
sorry.
get this over with. Okay, I might as well get this announcement now that I'm taping. Yeah, there will not be class, actually for quite a while after this. So not Wednesday, because I'm taking off early for my flight. And then no class next week at all.
Oh, so not even on Monday.
Right, not even on Monday, because we're still gonna be ahead. So, and that way we don't bother our substitute or anything like that. Yeah, but also, yeah, because Wednesday we still like nobody to be here, so, yeah, I'm just, not gonna bother. It's just easier that way. Okay. So, alrighty. So now we're getting into a new chapter. So definitely sometime between now and the next class, which will be November 2nd.
Yes.
I will definitely have homework 2 all graded and back to you.
Oh my god, I have to turn that in still. I'm so sorry. I'm almost done it, I promise. I forgot. I'm so sorry. I did start on homework 3 though.
Okay.
Before.
Well, that's good.
I'm so
So
sorry.
Bill turned it in, but well, yeah, but you're the second person in the class that turned it in, so
Oh.
yeah, I'm a 7. So
Yeah, but they're taking their test, so I understand.
yeah.
And I was kind of confused.
Yeah, really, what's your
about
excuse?
I suck.
You don't have enough.
I'm a terrible person.
I'm to be doing research, good research.
But that's not an excuse. I'm a terrible person too. But yeah.
Okay. So we've been spending all this time studying linear systems, and now we're going to use what we can of that for nonlinear systems. We're going to go back to nonlinear, but try to understand nonlinear systems using a technique called linearization, so we can treat it like a linear system, kind of. Okay. So the idea is we have a general nonlinear system, and we'll stick with autonomous systems here. Okay. But then we take a Taylor expansion of the vector field big X around some specific X value. So we can say x prime is big X of x naught, because x naught can be some point of our choosing, plus big X prime at x naught times x minus x naught, plus other terms which I don't care about. So what we can do is we just truncate it at this point, so we ignore all those Taylor series terms that I ignored anyway. I was too lazy to write. This is a linear system. So the idea is, since the linear system is easy to solve, if we solve that, then that helps us understand the behavior of a nonlinear system, at least locally. All right, so we'll solve this. To understand behavior of the original system, x prime is big X and little x. But again, as emphasized, it only gives us local behavior. So near x naught, whatever integral curves are for a linear system will be good approximations of the integral curves for a nonlinear system around that point. Okay. And this is what linearization is all about. We replace our nonlinear system by an appropriate linear system in order to understand behavior. All right. Now, to simplify things a little more, suppose that x naught be a fixed point of big X. So in other words, big X of x naught is 0. Well, that's just going to cause the first term to drop out. So what that means is, instead of looking at nonlinear system, so x prime is big X little x near x naught, we're going to shift to big X prime is equal to a big X, where the matrix A is this derivative right here. So basically, so this right here, I'm calling A. So here we have matrix vector multiplication. Near the origin, because so in fact, what I could do is, actually, to make it a little more clear, I'm going to use a different letter here. Instead of X, I'll use Y. Where Y is equal to X minus X naught. So that's what this becomes. And when X is equal to X naught, Y is 0. And because it's just a shift, a translation, Y prime and X prime are exactly the same thing. Okay, so by studying behavior of this system near the origin, we understand the behavior of this system near a fixed point. So that's what we're going to do in this section, is we'll take a nonlinear system, we'll figure out what the fixed points are, and then at each fixed point, we consider each fixed point separately. We'll take a look at this matrix and see what kind of system we get and what kind of behavior we get in the integral curves. So, nothing to it. Okay. So what's kind of nice is we're combining things we saw from last chapter about linear systems, which in turn built on chapter 3, and then also mixing out with stuff about fixed points from chapters 1 and 2. So we're seeing the author's nefarious plan. Okay. Now, before we go to the examples, we need to have an appropriate definition of this big X prime, because prime, and the funny thing is, the author uses this notation too, of taking a derivative of a vector value function of several variables. And I always tell my students in multivariable calculus, don't use prime for functions of several variables. It has no meaning. But I guess now it does. So what does it mean to take a prime of a vector field? And I guess it's pretty concise notation. So
why are we doing like near the origin?
Oh, because instead of near x naught. It's really more of a convenience. It's because of the Taylor series that we have this term right here. Because what we could do is think in terms of sticking with x and saying behavior near x naught, but then we get this extra term. So if we we stick with x and we leave this x naught here, we're going to get a non-homogeneous system. It's much easier to work with a homogeneous system.
Right, so you have x minus 0, which is x.
So we just call this a new variable.
Right.
Say, well, when x is x naught, y is 0.
Right.
Yeah. So it's just to simplify things.
Okay.
Yeah, because we could solve a linear system anyway, but okay. So, what is a matrix A, which is big X prime at x naught? It is the Jacobian matrix Those matrix are all first partial derivatives of all components of big X with respect to all variables. So for each row, we're taking partial derivatives of one of the component functions. So in this first row, taking the partial derivatives of just x1, the first component, with respect to all the independent variables, x1, x2, up to xn. And then, next row, I go to the second component function. Okay.
Big X's or little X's?
Yeah, that was my question. On top?
Okay, on top of big
Big
X's.
X's? Okay.
It's so much easier doing all this in LaTeX. Okay. And then finally, last component function with respect to all the variables. Okay. So each row deals with a component function. Each column deals with differentiation with respect to an independent variable. So in other words, Aij is a derivative of component function I with respect to variable j. Okay. So what we do is, at each fixed point, we'll go ahead and compute A. Oh, and I want to emphasize, we evaluate all these partial derivatives at x naught. So in the end, we're just dealing with the matrix of numbers. So we go ahead and compute partial derivatives in functions of like x, y, z, whatever, plug in the fixed point, and then just in for plain old linear system. Okay. So then what happens is, just like with linear systems, we need the eigenvalues and eigenvectors to solve the system, and like computed matrix exponential. But by looking at the eigenvalues and the sign patterns, or if they're complex, that can tell us behavior of the integral curves right there. So I need to introduce some terminology about the eigenvalues. So this is about classifying fixed points. Okay. Now, so the fixed point x naught can fall into these categories. And in some cases, there's overlap. It is a simple fixed point if A is invertible. So none of the eigenvalues are 0. Okay. Fixed point is hyperbolic. If the real part of every single eigenvalue is non-zero. Okay. Now, here we can break hyperbolic down into subcategories. The fixed point is a source if the real part of all the eigenvalues is positive. Because what that means is any integral curves near this fixed point are going to go away from it. Okay, so integral curves they will diverge from x naught. Okay. It's always showing up on the screen. Yes. Okay. Now, the opposite of that is we call it a sink. That happens if the real part of all the eigenvalues are negative. So in that case, no, the integral curves converge to x naught. So it's like a black hole in the middle of your solution space that's sucking in all the integral curves nearby. Okay,
So what happens if it's, some are positive, some are negative?
that's my next definition.
Yeah.
That is called a saddle.
Okay.
If the real part of all the eigenvalues are, so they have to all be non-zero, but if some are positive or some are negative. And just because if you graph the integral curves, like especially in a two-dimensional case, the graph kind of has the appearance of a saddle. And you have some integral curves, like basically they start converging to one of the eigenvectors, like one of the largest real part. So it just visually kind of looks saddle-like. Okay.
Did we talk about this in numerical linear algebra? No, we talked about saddle point.
Yeah. Points are different, right?
Yeah, okay. Sorry, I got confused for a second.
It's really more of a multivariable calculus thing.
Okay.
Yeah.
It sounded familiar and I was like, why does that sound familiar? But never mind, it was something else.
Yeah, okay. Yeah, at some point it all just sounds the same and blurs.
Yeah, the partial derivatives, if something happens, it's a saddle point. Right?
Yeah.
For max min,
Yeah.
saddle point, and that has to do with a sign of the eigenvalues of the Hessian. And I'm sure that's something I just like bringing up, so it's possibly to hear from me.
Yeah.
Okay.
Kind of weird deja vu.
Let's see. Okay, one more. A center. And I need to qualify this and say maybe. Oh, this is non-hyperbolic. I'm out of that category.
Is equal to 0?
Yes. The center. And it should say maybe. In the case where you have the eigenvalues are purely imaginary. But they're still going to occur in complex conjugate pairs, just because we're dealing with real systems, or like a real matrix. So what can happen is, you may have a case where integral curves form an ellipse. And we talked about the behavior before. When you have these complex eigenvalues, so if they're purely imaginary, that can happen. Because if there's a real part, you can have a spiral in or spiral out. So this is not that case. And the reason why I have to say maybe is, you can definitely say that the linear system has a center. So basically integral curves forming circles or ellipses around a fixed point. But remember, we're only approximating a nonlinear system. The nonlinear system is not necessarily going to have the same behavior. We'll have to get into that in a later section about how to really tell. If you have a center for a linear system, does that become a center of a nonlinear system? So we're just going to classify it as a possible center. And for now, the only way we can really be sure is to actually plot integral curves of your nonlinear system and see if it really does behave that way. Okay. So what we can do is now we'll go through an example of looking at a nonlinear system, look at its fixed points, and see how we can classify these. So we'll start a two-dimensional case, and then we'll move to a three-dimensional one where we can learn about more kinds of behavior and understanding integral curves is even better.
Will we be able to leave our needs?
That might happen. Well, okay, down to the bottom of the first page, let's go for this. Except I have stuff not written on these,
Right.
just to do the example, but we'll see. Yeah, I'd be fine with that too, because then I get to go home. Okay.
You going to work?
Okay. Now, so here we have an interesting application. A predator-prey model. So the general form is this. Okay, so we have CX minus Y, where X and Y represent populations. So X is the population of the prey, and Y is the population of the predator. Okay, and all these constants have meaning. So A basically is the birth rate of the prey, because if you ignore the predator, like if you forget about this Y term, if X prime equals AX, that's just standard population growth, which tends to be exponential. But this term of minus BY takes into account that some of the X's get gobbled up. So B you can think of as a predation rate, basically how likely is X going to be gobbled up by Y. Now, the more predators you have, the more likely you are to get eaten. So that's why we have the factor of Y in here. So this is like rate of predation per predator, and then you multiply it by how many predators, and then you have your real likelihood of getting eaten. And of course, that's going to knock your population down, so that's why I have a big old minus here.
That's kind of cool.
Yeah. Yeah, and then similarly for the predator, so C is prey rate, so how likely are we to get an X? And the more prey there is, the more chance you're going to get food. So that's why the X is a factor there. But we have the minus D, that is the death rate
Of the predator?
of a predator. And the thing is, if D is too large compared to C, then what can happen is starvation. There's not enough prey around to subsist. So what's really interesting is if you go ahead and solve this system for particular values of A, B, C, and D, you can see, well, which population is going to survive? Are they going to sustain themselves? Just this mutual agreement that you eat some of me and you survive, and then we reproduce enough, and then we give you a food supply? Or is there going to be because what could happen is, let's suppose that A is not large enough. So what could happen is
D could increase, right?
well, D is fixed, but the thing is, it could cause its population to decrease. There's not enough food. Is one population going to die out first? And what if this population is growing quite a bit? Is that going to also keep grow even more? Which one's going to win? We're both going to win. It all depends on the kind of behavior that you get. So actually, that's just something really interesting. Try this out for numerically, like for different values of A, B, C, and D, and see which wins. This is the most common models of Lambda Volterra. That's what this is. So, if you're interested, you can Google that. And you'll probably some information about or results like if the constant's related this way, this happens to the population. Okay. Actually, let me make sure I got that right. The names. I definitely know the second name is right, but Lot. Yeah, I got it right. Wasn't sure if I transposed letters in the first name or not. Okay. So what we'll do now is we'll take a look at specific values of A, B, C, D, and see what happens. Okay. So we'll let x prime equal 10 minus yx, and y prime is x minus 50y. Okay. So first, we need to find the fixed points. Okay. So what would be the fixed points? What values of x and y would cause both derivatives to be 0?
Sorry, what was the question? I was copying it down.
Oh, what values of x and y would cause both x prime and y prime to be 0?
Well, then we want to solve it, right?
Yeah.
Well then, because 10 makes x prime, y equals 10 gives x prime 0.
Yeah. Okay, but then if y is equal to 10,
I mean, does it matter what x is equal to?
in this case, yes.
50.
Oh, 50, sorry.
Yeah, so that's one fixed point.
Right.
And what's the other one? There's one more.
0, 0.
Yeah. Pretty. Yeah, so it makes sense that if full populations are 0, then it's supposed to stay at 0 for all time.
Right.
There's no eating going on at all.
Right.
On the other hand, what's interesting is if so what happens is if there are 50 x's and 10 y's, then what happens is the population will stay that way for all time. It'll be a perfect balance. So that's when. So when you have an interesting fixed point, that's when you have these stationary solutions. Okay, so now what we can do is take a look at the. So if you look at this, if x prime has a function of xy, so what we need to do is take the derivatives of these with respect to both x and y. All right, so derivative of this with respect to x.
10 minus y.
Yeah, and with respect to y.
-1. Oh, negative x.
Yeah. Right, and then derivative of this with respect to x.
Well, with respect to x, it's just what? Y.
Yeah, and with respect to y.
X minus 50.
Yeah. Okay, so now what we'll do is compute the, we'll plug in both of these fixed points. So we'll plug in 0, 0, and we get, let's see, 10, 0, 0, minus 50, and then at 50 and 10, okay, so we get 0, 0, minus 50, and 10. Okay. So now in each case, we need the eigenvalues. Now, the first case is easy. That's the diagonal matrix. So the diagonal entries are the eigenvalues. So we have 1 equals 10, and 2 equals minus 50. So because all the real parts are non-zero, this is a hyperbolic fixed point. How would that be classified?
Source, right? Well,
No.
no. Well, saddle.
Yeah, because we have a
Because
positive
one's-
and a negative.
Yeah.
So it's minus 50, so that is a saddle. And then over here, we can't just read off the eigenvalues because there's nothing is diagonal. But because the diagonal entries are 0, that means the trace is 0. So the eigenvalues sum to 0, so they're negatives of each other. But what's the determinant? The determinant is 500. So that means, but if you have two numbers whose that are negatives of each other, but their product is a positive number, what's the only way that can happen?
What?
Two numbers are negative of each other, so they're opposite sides, but their product is still a positive number. So that seems kind of odd.
Is that imaginary number?
Yeah, purely imaginary.
Bam!
Yeah.
Sorry.
Yeah. So the eigenvalues are equal to plus or minus I times the square root of 500, which is 10 square root of 5. Okay. So how do we classify this kind of fixed point?
Oh, is that the last one?
Yeah, it's a possible
Center.
Yeah, so it's
Maybe.
a possible center.
Center, maybe.
Yeah. And in this case, if you were to plot the integral curves of a nonlinear system, you find it really is a center. Okay.
So how do you get plus minus I 10 square root of 5?
Oh,
So it's like the square root of 500.
Yeah, I
Okay,
just
okay, yeah.
Okay. So what would this mean for the integral curves? We can do a rough sketch. Well, first of all, in this first case of 0, 0, because it's a diagonal matrix, the eigenvectors are easy to see. It's just like x-axis and y-axis. So in that case, the way the integral curves would behave around 0, 0, because this eigenvalue is positive, it's that x-axis eigenvector that's going to dominate. The solutions near 0, 0 are going to converge towards the appropriate part of the x-axis and move away from this negative eigenvalue. So here, the eigenvector for this is just the x-axis. The eigenvector for this one is the y-axis. This eigenvalue is larger, it's going to pull the integral curves toward it. So that's where you get the saddle-like behavior around the origin. And actually, I need to check, make sure if it disagrees with the picture in the book, because I don't remember it. But, okay. Ooh, I got it right.
So since that's greater than 0, that dominates and makes it go away from the 0, from the origin, right? From the fixed point.
Right. Yeah, because you have an yeah. So along this direction, it's acting like a source.
Okay.
Yeah. Okay. Now, the other fixed point. So x is 50, y is 10. So that's over here somewhere. The integral curves behave something like this. At least near the fixed point. Once you get far enough away from it and over here, then the behavior starts to become more like this. So what that means is solution curves near a fixed point orient like an orbit around it. So what that means is, yes, there's fluctuation in the population, but it never gets out of hand, as long as you're close enough to that fixed point. So there's this ebb and flow in both x and y, like a cyclical behavior. But let's try it. Now, the thing is, we should only consider x and y being positive, because I would hope we would not have a negative population unless maybe if you consider zombies.
Yeah.
Ooh, okay, now we have a more sophisticated model. So yeah, we have some extra terms in here for zombieage.
Right, probably E, or like
Yeah.
introducing
Oh my
E for
gosh.
zombies.
Just start writing a paper on, predator prey models and like
Introduce
looking
zombies.
at them and introducing zombies and like negative X. Oh my gosh, that'd be so cool. Okay,
Yeah,
keep going.
because this is predator prey for the living.
Yeah.
And then you have different terms, and this is not to focus on like if the population is positive or negative.
Yeah.
Okay. Ooh. I'll see if anybody's done that, but if not, then we should.
We should. I think that sounds like fun.
But then zombies, then you're talking zombies.
I know, but like I
Yeah.
feel like there's a nerd population out there that like would appreciate that, and it's math, so
Yeah.
like they're all nerds.
You could,
Yeah.
consider the possibility of zombies existing.
You
Yeah.
would you would read a paper like that, right?
Yeah, and I would enjoy it if you
Yeah.
understand. Yeah.
Whereas if you're over here somewhere, because, well, actually, I'm not sure how it's going to behave. Because the linearization is not going to tell us anything about that. So I have no idea. But like if you're over here, for instance, it's close enough to the origin. So in that case, both populations are pretty small, but they're going to tend to this, where the, actually what's going to happen is the prey is going to win. This population is going to go up to infinity, and the predator population is going to go to 0. That's really weird.
Because, say if there are like 3 predators and 3 preys, and preys are generally faster. Well, not really. But, so if there are 3 predators and 3 preys, the prey wins.
No, that makes sense because if there are too much prey or whatever, the predator still. Oh gosh, I saw this on like National Geographic or something.
Yeah.
I read it somewhere. It's like the prey takes over the population and takes up all the resources and everything like that, and so
Yeah.
that's why the population of the predator goes to 0. There's too many prey, I think.
Yeah.
Right?
Yeah,
Isn't that a thing? That's a thing.
Even if the predator eats up, it cannot eat up enough prey, and they
They just take over
eventually
the
die,
predator.
and they're
Yeah.
probably
I can see physically how that would make sense.
they're probably
Yeah.
more sad.
But mathematically, it's kind of weird because here what's happening here is, let's suppose x and y are both small.
Yeah.
And, with this example, we have the numbers filled in. So y prime is having this, very bad negative exponential term.
Mm-hmm.
So we're very likely to die. And then the so the population x has to get large enough to be able to offset the tendency of a predator to die.
Yeah, the death rate for this exact predator is high.
And if the population of x is small enough, then what's happening over here is because the reproduction rate is greater than the y, then this population is going to grow. And but if it never reaches critical mass, then this will still overwhelm it. So what happens is, on the one hand, interesting.
So the birth rate is high.
Let's kick everyone out of class more often.
What?
Let's kick everyone else out of class more often.
Yeah.
No, because
So
it's 10 minus y times, but if it's like, I don't know, if it's like a high birth rate and the predator is like fairly small and so is the prey, the population, then how does it make make everything, like the prey bigger?
because on one hand, if for integral curves, if you were, as soon as you get to this territory, we need to go into orbit, the populations balance each other out.
Right.
Yeah.
So you go. Okay.
Yeah, so the trouble is you need enough prey to subsist to support the population of a predator.
Predators.
So,
Yeah.
Interesting.
Right. Right.
So, again, the thing is, the book doesn't show anything more than this, but the integral curves, it'd be interesting to try plotting integral curves away from these fixed points. Like, what would the other behavior be? Is there a situation where the integral curves both zoom off to infinity, and then the whole world is overrun with predator and prey?
Right.
I don't know. Okay. So, I think this is a 2-dimensional example, but you can study 2-dimensional systems in other ways. You can, we covered that before actually with regard to fixed points to see how integral curves behave. But doing this linearization is actually more informative for higher dimensional systems. So we're going to look at a 3D case now, where it's more difficult to plot things, but you can still understand the behavior. But first I need more, actually, I think it's better to do this in the context of the example, because if I try to, I'll have the abstract definitions in the notes, but to say it's something formal, which the book never provided. But at least it's easier to see from the example how these things actually work. Okay. So we have this 3D system. Okay, so what are the fixed points of this system? Because x, y, and z prime would be all 0.
0, 0, 0.
Yes, that works.
All right, your turn.
Well, y is what? 1,
Uh-huh.
and x is -3, and z is 2.
Okay. And there's
Another
another
is y is -1,
Yeah.
and everything is the same
Yeah.
because it's the y squared thing.
Yep. Okay. So those would be fixed points. So now we need a Jacobian. So x prime of x, y, z. So what are partial derivatives of these? So starting with this one, with respect to x and y and z.
Okay, I'm still writing. I'm sorry.
What are the partial derivatives?
So starting with this first one.
Well, that in terms of x is just that guy, right? 1 minus y squared.
Yeah.
And then you want what? Then you want
With respect to y.
well, -2y, x.
Yeah.
2x,
Okay.
y, yeah.
And then with respect to z.
0.
Okay. All right. On to the next one.
So with
0. No,
x,
not
it's
0,
z,
Uh-huh.
and with y, 0. And with z, it's x plus 3.
Okay. Finally.
0.
0.
And with respect to y, z minus 2, and then it's what? y.
Okay, so now we can plug in the fixed points. Okay, so starting with the first one, x prime 0, 0, 0. So just plug in everything 0.
Or 1, 0, 0, 0, 0, 3, -2, 0.
Okay.
Wow.
All right, so that's our Jacobian at this fixed point. So because of the decoupling here, 1 is an eigenvalue. Now here we have a similar situation as in the previous example. Elements off the diagonal and of differing signs, that's going to be complex eigenvalues again. So the other eigenvalues are going to be purely imaginary. So it's plus or minus square root of 6 identity. So what that means is,
Identity?
what?
You said plus or minus square root of 6 identity.
Oh. Plus or minus square root of 6 I,
I'm sorry.
imaginary unit. Okay, mix up my I words. Okay, so in terms of behavior of a fixed point, it's kind of weird because, because we have any purely imaginary ones, this actually leads to a center.
Then you have a real one.
And the consequence of a real one is going to cause a spiral. It's called spiraling along the x-axis. And the reason it's the x-axis is because the eigenvector for this eigenvalue is 1, 0, 0. So what happens is in the also along the x-axis, there's going to be a spiraling, except at the origin. So y equals z equals, so in the yz plane, then we have a circle. So it's not, the spiraling along the x-axis stops at that point. It just, so if you have a solution that's in the, I'm sorry, not y is at x equals 0, then we have this circle in the yz plane. Okay, because of those purely imaginary eigenvalues. Okay, but away from x equals 0, but y and z still 0, the spiraling is going on because of that positive eigenvalue. Okay, now the next Jacobian.
Where do you go the thing for the 2 plus minus? Sorry, plus minus square root of 6. Where do you?
That's good. Yes, it doesn't really show I'm drawing here, but if I do a different view, here's your x-axis.
Yeah.
So here at x equals 0, this plane, we're going to have orbiting of a fixed point. So the thing is, because only the yz eigenvalues are purely imaginary, that's why the orbiting happens only in the yz plane. Whereas if we had all purely imaginary eigenvalues, which actually is impossible for a 3D system, you'd have like a sphere orbit. Okay. Right. Next fixed point. So x is minus 3, y is 1, z is 2. Okay, well, let's see. Some of these entries are 0 anyway. And then that's going to be 0, and that's going to be 0. Y is 1, and then this is 0. Okay. 6, and z is 2. Okay. So what happens in this case, because these have same signs, you're actually still going to have real eigenvalues. So what happens in this case, so lambda, we still have an eigenvalue of 1, and then the other eigenvalues are equal to plus or minus square root of 12, so 3 square root of 2. Okay.
Is it 2 square root of 3?
Yes. Otherwise that'd be 18, wouldn't it?
18. Good.
Man, I'm just...
Today is the best day ever for me. I'm sorry.
A lot of caffeine or something.
I have.
Well, the funny thing is, like, yeah, you're posting this morning, you're wondering if your program's working or if you're a raging idiot.
Yeah.
And if you knew the outcome would be, I would be. So, okay.
So how do you get lambda 1 equals 1?
Oh, because of the decoupling
Okay,
in
yeah.
the block diagram
Right.
form.
Okay, so the left one, and then
Um,
the left, that guy becomes.
Yeah.
Okay.
And this eigenvector is along the z-axis.
Right.
So because of the eigenvalues, what kind of point is this?
Well, a source or saddle, right?
Saddle, yeah.
Because there's 1 negative 2.
Okay. Okay. So that's all of the interesting behavior we have at this point. And finally, the other fixed point is, okay, y is minus 1. And the only effect that's going to have, the matrix is going to be exactly the same, except
Negative 1.
no, up here, that's going to be a minus 6.
Oh.
Okay.
But then y would still be negative. Oh.
Yeah.
Because that y would.
Oh.
Yeah.
Right.
Negative 1. Oh.
Oops.
So you
Okay.
saw that 1.
Wow, that's messing them all over the place. But I just want to see it to be over. So. Okay.
You're trying to keep us on our toes. I get it.
Yeah. Okay. Well,
Thank you.
well, at least you're on your toes. Okay, so the eigenvalues, the first one is minus 1.
Both are.
And now these are going to be complex. So it's going to be plus or minus 2 square root of 3 imaginary unit, not identity. So what's going to happen this time?
Center, but.
Yeah, there's going to be a, I realized 2 and 3. So there's going to be a center at the center in the xy plane where z is equal to 2. And so you're going to have this spiraling, a situation like this, just in a different plane. And also you're going to have, because of this eigenvalue of -1,
Sync.
no, you can have a spiral
Oh, yeah. Only one. Oh, yes, right.
along the z-axis. Okay. All right. However, one difference, the difference that the sign is going to make, in this case, it's going to be converging. Let's see, toward the origin because of a negative eigenvalue, as opposed to away from the origin in this case. So that's the difference that the positive versus negative eigenvalue makes. Now, hold on, 10 minutes left. Okay. Now, let's see. Now, this case. Oh, okay. Right, that's going away. This is going toward. Yeah. All right. Okay, so at least we have some understanding of a behavior from the fixed points, but there's more we can understand about the system than just that. And that gets to what are called, so instead of, because here, in this system, fixed point, all 3 derivatives are 0. What if only 1 or 2 of these derivatives are 0? So then when you have, instead of a fixed point, you have like an invariant line or invariant plane. So you have like in the previous homework problem, you have to find fixed line solutions. Yeah, so this is how you can find those.
Homework 4?
What? What?
What homework are you
The very first one.
talking? Oh,
You had one problem where you had to solve a system explicitly
right.
and then find fixed line solutions.
Yeah. The X primes and all those.
Okay. So by studying just the derivatives, like without solving a system, you can find fixed line solutions. Okay. Not all fixed lines, but certain fixed lines anyway. Okay. So, all right, I'm going to repeat the system here. Okay, so invariant lines. So here's what you can do. To find invariant lines, you can set x and y equal to certain specific values in order to make x prime and y prime both equal to 0. Is it possible to do that? Okay. So can you find? So in other words, you're not allowed to substitute for z.
Right.
Leave z alone, but find values of x and y that will make both these first 2 equations 0. Don't worry about
X
this.
equals -3 and y equals 1 or -1.
Yeah. So x equals. So in other words, you have 3 plus or minus 1, and then z is a z.
Even
So-
negative?
What?
Even
Oh,
negative.
-3. Yeah. All right. Okay. So that's 1. So this is. These are 2 invariant lines. So the idea is, what happens here is the equation for z reduces to z prime is equal to plus or minus z minus 2. So you're going to have some exponential behavior for z, but it's going to stick on the line x is equal to -3 and y is equal to plus or minus 1. And z is free to vary along that line. So you can only find invariant lines in this way that are parallel to an axis, but that's still something. And you don't have to solve the system. That's the best part. Okay, so this gives you two invariant lines. Now, to find another invariant line, let's consider setting x and z equal to something in order to make the equations x prime and z prime equals 0. So don't substitute for y, only substitute for x and z.
So z equals 2 and x equals what, 0?
Yeah.
Right.
And then y is not substituted. So when x is 0, z equals 2, that is another invariant line. Okay. And finally, can you set y and z equals something so that y prime and z prime are equal to 0? So,
They both equal 0.
yes.
X 0,
Okay.
0? Yeah.
Yeah, so in other words, along the x-axis, that is an invariant line.
So the x-axis.
Yeah, because x itself, because then you have x prime equals x. So along that x-axis, the solution must be x equals e to the t times a constant, but y and z will remain fixed at 0. So the solution will just so the solution curve actually is the x-axis. Okay, so those are invariant lines. So if a solution curve touches one of these lines, it has to stay on that line. Now, it may travel towards or away from the origin based on the behavior. Like in this case, because of x prime equals x, it's going to travel away from the origin. Whereas in this case, because z prime is equal to plus or minus z, it'll travel either toward or away from the origin depending on which side it is.
So if it's plus, away, negative, towards.
Yes. And then this one, you have y prime becomes, okay, x is equal to 0, so y prime is equal to 6. So that means that y of t is equal to 6t. So it's going to travel, well, for positive t, it'll just travel away from the origin.
Mm-hmm.
Then negative t also away from the origin. Okay. Last thing, because we're almost out of time. Oh, very much almost out of time. We also have invariant planes. And in invariant planes, the idea is you can set x equal to something to get x prime equals 0, or y, or z. Now in this case, there's only one of these possibilities that will work.
So x equals 0.
Yeah, so you can set, so the only invariant plane that we have is x is 0,
0, y, z.
and then, okay. Now, the thing is, once you do that, let's look at what the system reduces to. So x prime is 0, and then y prime is equal to 3z, and z prime is equal to y times z minus 2. So now you've reduced it to a two-dimensional system, where x is fixed at 0. So now you can, for instance, you can consider fixed points. Like a fixed point would be z is 0, and y is equal to 0. So it contains that origin. You can also look at this scaled-down system for invariant lines. So an invariant line of this system is you can set z equal to 2, and y is untouched. Okay. Oh, shoot. There is, I goofed. There's one more invariant plane. one more of these situations that can work out. You can look here.
Y equals what? Z?
Z.
2?
Z equal 2.
Oh.
Yeah, so Z is 2, and then X and Y are unassigned. So now that system scales down to X prime is still the same thing. Y prime is equal to 2 times X plus 3, and Z prime is equal to 0. So now you can study this system to see where there are fixed points. Like here, you can get fixed points at X is plus or minus 3, and then X is equal to minus 3, and Y is plus or minus 1. And also, you can look at invariant lines. So in this case, all you can do is set X equal to 0.
So can we not get also, yeah, like X equals 0 gives you a fixed point?
Sorry.
Okay.
Wait, how does X equal 0 give you a fixed point?
What? Not, oh, here?
No.
What were you
like
talking
for the
about?
top part. Yeah, for the top part, if you set -3, X equals -3, you get a fixed point because Y prime is 0. But, right?
As long as you also set Y to plus or minus 1. Fixed
Yeah.
point, everything has to be 0.
Everything has to be 0. Okay,
Yeah.
okay,
Yeah.
right.
For an invariant line,
Right.
all
Invariant line, okay,
um,
I'm probably thinking.
invariant line, you just need one of these to be 0.
Yeah.
Right.
With
Okay,
from
cool.
the appropriate variable.
So which is X is 0 and Y can be in it, yeah. Okay. And how about invariant line? This is Y and 2 because,
Yeah, now keep in mind, I'm referring to
Right.
Y and Z coordinates here. I'm scaling down to 2 dimensions.
Right.
X is out of the picture.
right.
And in fact, what's happening here is your invariant lines here are 2-dimensional projections of these invariant lines. Really. So, yeah, so that's what you can do. If you can find an invariant plane, you can just reduce the dimensionality of the system and see how it behaves along that, within that
Yeah.
plane. Okay. And, I've gone a little bit past time. Okay, but I got through all the section.
Yeah. Like for the next homework, there's like 9 problems, like 8 or 9.
But I'm hoping these are more merciful. Really,
Okay,
it's
yeah.
more complicated.